András István Nagy. Andras is a hands-on solution architect who likes building usable software. He is interested in challenges of scalability and distributed data processing and working on cloud-native software. So please welcome on stage András István Nagy. The title of his presentation is Finding Bad Bees in the Hive. So András, the stage is yours.
Hello, and thank you very much. Good evening, everyone. Good morning, good afternoon, depending on which time zone you are. Welcome to my short talk. So my name is Andras. Today I will be talking about detecting anomalous behavior in IoT devices. So IoT devices are a little bit like bees that are autonomous, but also belong to a larger system and show lots of common behavior. So what we set out to design and build was an anomaly detection solution with a unique challenge that it has to work for devices in any domain, from health trackers to intelligent cameras to home alarms and so on. Why is that? So our customer is one of the major IoT platforms with tens of thousands of businesses providing IoT solutions with tens of millions of devices on this platform. So the product team behind this platform decided to build an anomaly detection system for the network usage of devices on their platform. So that is providing a monitoring system that is able to learn the communication patterns of devices and then alert the customers if their devices seem to behave strangely. So let's first look at a few examples of how this can be useful. So as an example, imagine that you are building a patient monitor system using IoT appliances. Your device monitors dozens of signals of patients, records them internally, and then publishes them to your patient tracking solution regularly. And assume that in one of the firmware upgrades, you misconfigured something, and the vital signal that used to be published every 10 seconds is now only publishing it every 10 minutes. So your system still has that signal. So you may not notice, but the additional latency may be absolutely critical to the patients if something happens. Or as another example, imagine that you have a business that develops really intelligent vending machines that serve drinks and sandwiches and stuff like that. So these machines need to keep track of stock to see if some product is sold out. They need to keep track of how much change is available to return and so on. They have been designed as intelligent IoT devices that connect to your cloud system. And now imagine that there is a security hole in one of the libraries that you are using, and someone finds that and then turns your entire fleet of machines into a hacked botnet. So let's say they want to use your 20,000 internet connected devices to attack a site and bring it down with a DDoS attack. Your devices still do their job of serving tea and snacks and report if something is out of stock. So your device management system may not even notice for some time that something is wrong. So what is common in all of these cases? Something happened with each product, but if their monitoring systems focus on functionality, they may not detect that anything went wrong. What's common in all of these problems, though, is that the device's communication patterns changed. Like there was a sudden peak of network traffic when the vending machines were taken over and sending millions of network requests to a targeted website. Or in the case of that patient monitor, there was a regular pattern of traffic, but that changed its frequency. And these problems are apparent at the low level, at the layer of communication over the mobile network. So potentially these problems can be captured by analyzing device behavior at the network communication layer. So on a very high level, there were two major challenges in this project that we had to solve. So to begin with, our goal is not to detect network usage anomalies for vending machines or intelligent cameras or health monitors. Our goal is to detect anomalies in all of them, and that's a big difference. So having tens of thousands of customers on this platform in every conceivable domain meant that we needed to design a solution that is generic enough to apply to all of these customers in all of these domains. But at the same time, it can learn so as to become specific enough for any of them to be useful. And even though we had a really awesome data science team, still that's a very hard challenge because these devices are substantially different. With a metaphor, you can think of this as a system that has to detect imposter bees in a hive, and one that has to apply to wasps as well, even though wasps are quite different beasts. But finally, it has to apply to potatoes just as well for the metaphor. So anomalies can be detected only if we can infer a pattern, and then later we can compare the actual behavior to the learned pattern. And some of the customers have completely autonomous devices, with very predictable traffic patterns. Some are driven primarily by humans, resulting in more unpredictable patterns, and some are in between. And naturally, this sounds like a good use case for machine learning, but it was a hard challenge from a data science perspective. While each of these domains could be served by a targeted machine learning model, we had to implement a solution on an IoT platform level to make it applicable to every customer. And this meant that we could not build any domain knowledge into our model. We had to make it very generic. So the other challenge was how to get sufficient amount of data, resolution of data about these devices so that we can actually train a machine learning model. So for each device, we only have a few observations a day, between 2 to 20. So what can we do to increase resolution? So we can increase resolution in time by using a longer time period to collect training data. But there is a trade-off there that the model has to be able to adapt to changing patterns quickly. And the longer historical period we use to train, the slower it is for the changes in behavior to be able to dominate the training set. Another trade-off is that we can't wait for a year to have enough data to train models because the users of the platform need this functionality now. So if we take a whole group of IoT devices that work in the same domain, we can also get more data on their network usage behavior when we combine them. Now, of course, behavior is not constant across devices. It's not even constant across devices that are of the same kind. So we must be able to group devices based on their behavior and then train models separately for each group. Now, taking our patient monitor example, the device is configured for, let's say, high resolution monitoring of patients at intensive care will produce very different traffic patterns than the same devices that have been configured for patients that have already been released to their home. But for us on the IoT platform level, such differences are not visible because these are at the application layer. So we have to find a way to infer these different groups of devices directly from their traffic patterns if we want to be able to detect anomalies in these patterns. Now let's first have a look at the overall architecture to see what we are doing on a very high level. So the goal with this design was to build a scalable and cloud-native architecture in Amazon Cloud. Our input is arriving as network usage events. They get pre-processed by a data pipeline, at which point we also have to run some data quality checks and log data issues and data observability metrics. But the more interesting stuff is happening as these pre-processed usage rate events are handled by the machine learning models. And for this purpose, the same events go on two paths. So first, they are feeding into our MLOps pipeline that takes care of training the models and rolling them out every week. And the same events are also feeding into real-time inferencing, where we have a Lambda that processes each event and then uses these models to determine if those events look anomalous or not. We also have live monitoring, model monitoring component, which is aggregating metrics on the ML model performance and logs the results to trigger alarms if needed. And then finally, these detected anomalies are going to the customers as alerts about their devices. Now, speaking about specific technologies, we don't have anything exotic really. We rely on a bunch of serverless AWS services and a streaming data pipeline using Kinesis data stream as its backbone. So our input is arriving as batched network events through API gateway, which publishes them to a Kinesis data stream. The pre-processing is done by a series of Spark jobs running in AWS Glue. And we also have a Lambda here that is doing the feature extraction, and it is the component producing our usage rate events per device into another Kinesis data stream. In our MLOps pipeline, we are using SageMaker model building pipelines to train the models and to roll them out every week. Now, looking into the machine learning part, let's see what were the high-level drivers for the design here. So first, this is a large platform with really a constant stream of network usage events from tens of millions of devices. So it was essential that the model be simple enough to scale to this size. The second, the device's behavior changes constantly. So our system must be able to learn these changes by constant retraining. The third, as I mentioned, the solution must be generic enough to be applied to any set of devices. This means that even though we did use data from a few selected customers to develop the solution, that data was used mainly for exploratory data analysis and for doing research and POCs. But we had to make sure not to build on any conclusions that were customer specific. And finally, the system needs to alert customers when it sees that their devices are anomalous. And here we aim to minimize false positives more than false negatives in order to minimize noise that this system produces. This meant that our solution needs to be also conscious of its limits. So we need it to be able to tell when it's just not possible to detect anomalies with a very high confidence. An example of that could be when device behavior is always very unpredictable. In that case, it's difficult to differentiate an anomaly from just the regular noise. So the high-level objectives we have seen in the previous page determined our approach to the problem. Now let's focus on the ML pipeline we have built when implementing this in practice. So first, what is an ML pipeline? It seems like almost everything in a data conference is about pipelines, right? There are data pipelines, deployment pipelines, ML pipelines. Actually need all three. So we have a data pipeline that I briefly talked about when we looked at the high-level architecture. It is the one that takes the raw input data, transforms it to conform to our model of hourly time buckets, and produces usage rate as the input feature of our model. And then we have our ML pipeline, which takes this input data and the code that we develop to model our problem space. And this ML pipeline produces the trained model instances. Now, in our case, all model training is done online from scratch every week in the production system itself by an automated process. So we train the new model instances, and after validating them, we roll them out to production. And then finally, to close the loop on these pipelines, we are also monitoring the models as they are used to make decisions so as to be able to detect if something seems off. And in our case, we needed one additional step in the beginning of this pipeline, the device clustering. Let's see what it means and why we need it. So this is the step that helps us to get sufficient data to actually train models by putting devices into groups. So we want to put those that show similar behavior into the same group. We are looking at behavior on a weekly scale and at an hourly resolution. So as we have seen, the reason why we need to do this is that we just don't have enough data to actually train models for each individual device for each hour of the week. So we are using an unsupervised ML algorithm to cluster. That is to find those devices that show similar behavior and put those into the same group. And as a result of this, we get these bigger clusters of mostly homogeneous behavior, which gives us enough data for each single hour to train a model for anomaly detection. What is this data actually that we are clustering? For every 168 hours of 1 week, we have a calculated usage rate for each device. That is, one device is represented by one data point in this 168-dimensional space. And we are looking for these devices that are behaving similarly, so those that are close together in this space. Our data science team has evaluated multiple clustering algorithms and metrics and has found that a density-based clustering approach fits the problem the best. So with those approaches, we are not taking a most typical device, let's say per cluster, like a cluster centroid and others that are within a close range of that. But instead, we have these more or less defined blobs in this space, which are areas where points are more dense. And the algorithm that seemed to best match our use case was HDBScan, which is a hierarchical density-based clustering algorithm, and DBCV as a density-based evaluation metric to choose the best assignment of clusters. Now, the visualization that we see here is showing a specific example of this clustering by mapping the original 168 dimensions into 3 in a dimensionality reduction process, and identifying denser areas as behavioral clusters, which are marked with the same color. And we have outliers here marked with blue. Now, after we have identified groups of devices that show similar behavior, we are combining those devices' data to have enough data to train a model. The model we use is called GMM. It represents a mixture of normal distributions because research has shown that network usage rate follows this pattern. More precisely, it's the logarithm of the usage rate, which follows this distribution. So the results represents the usage rate as one or as a mixture of 2 or more log normal distributions. And finally, it is this model that gives us the means to identify anomalies. Because when we get the new observations in real time about the devices, then using these pre-learned distributions, we can calculate the probability of that new event. And we defined an anomaly as an event that's unlikely to happen. So if the probability, the calculated probability of an event falls below a threshold, then it means that we have found an anomaly. Now let's briefly look at how we organize the data science work. So first, we started by implementing model validation. This meant a lot of design and research on what are some very targeted custom metrics that quantify how well a given approach works. So that is using one approach to anomaly detection and device clustering, how well does that apply to historic data? So later, when doing the actual research and design where to find suitable clustering and anomaly detection solution, we already had a solid implementation for this model evaluation that help us to measure how well a given approach works. To develop these metrics, these validation metrics, we had some production data from 3 customers covering 3 months, but as I said, this was only partially useful because it does point out certain issues that are potentially present in the data, but it is a question how well it generalizes to other customers' data. And also it is not labeled, so we don't know upfront if there are any anomalies in this data. It's just a huge data dump from a few customers with no additional information to compare our results to. So to address these limitations, we implemented a device simulator, which is able to simulate a large number of devices that can be organized and configured in groups with different behaviors and different changes of behavior over time. And that allows us to create artificial scenarios where we can define the expectations towards our system. So with that, we actually have data that allows us to reason about our solution's capabilities. That is, how well it is able to handle one specific scenario. And we are using these simulated scenarios in research and also in model development. Now, I put here an example scenario that is quite similar to those that we are using in these test cases based on simulated data. So in this one, we are testing the effects of a trend in the source data. We are defining a training period with an increasing trend in network usage for 3 weeks. And we define that the same trend should continue in the 4th week, which is the one that we use to test the system's response. And we define our expectation for our system's response, in this case, for no anomalies to be detected. And this approach allows us to test our solution's behavior in these well-defined scenarios. And as we see new examples in real life, in actual production data, we extend this suite of tests. Now let's summarize what we learned from this work. So I think the biggest learning is that productizing or productionizing a machine learning solution is difficult. Why is it? So first, data science tasks are mostly research. So they are inherently badly plannable. In the end, the outcome is either that it worked out or that it didn't. If it didn't, you need to look for a new approach. You actually don't know how many times you have to repeat. That's the research part. You don't know when it will end. But this is actually not a surprise. It's a well-known thing. It's also a reason why data science projects use custom methodologies like CRISP-DM, and why many agile methodologies don't really work well with data science projects. Now, also a consequence of this is that we have to do data science POCs and spikes as early as possible. If possible, then before actually committing to a delivery deadline, obviously. And next, a data science POC it's not a production solution. And also the skills needed to productionize one are different than the skills needed to do research. We actually were extremely lucky to have some really great data scientists that could do both. But still, mostly these are separate skills. And next, our MLOps process is not the most typical, because what we have is not a few complex models that take a very long time to train on some carefully maintained data set. In contrast, we have very simple models, but we have a huge number of them, and we train them constantly on just whatever data happens to flow in. And that's just not what the current tools optimize for. So automation around training and productionizing models does exist. We actually do use a lot of automation from SageMaker, but in general, this field is quite immature yet. And finally, we can confirm as good learning that starting the data science work with building the validation code did pay off, because it allowed us to progress faster on research tasks. It is like test-driven development applied to data science, and it did pay off. So I summarize that as starting with the research for proper metrics for evaluation of the models on historical and simulated data. And that actually worked well. So I think with that, my time is mostly over. I would like to thank you for your attention. I hope there was something useful or interesting for you in this talk. And if there are any questions, I'm happy to answer.
Thank you very much, András. You have an impressive set of guitars behind you. Are these all of them, or you have more?
I have a few more, but I just wish I had more time to play.
Okay. So thanks for the presentation.
Yeah, thank you very much for the opportunity.
We do not have a